that's 8th grade. That's not helpful. There is 11th grade. That should be helpful. Yeah. Today is the 9th. 9/2. This is, what do we got? 11:30 to 12:15. On a snowy February day. Hello. Tell me who you are. My total physicist. It's Ellie. Well, that's a surprise. Always my first one. Good morning, Ellie. Glad you're there. Okay, who else I got? I got Anne-Sophie. Hi, Anne-Sophie. Glad you're there too. And I see 3. Let's see if somebody else is there. And now 4. So I'm assuming that's everybody. Let's see. Sometimes Teresa has a hard time responding. So let's see if she's there or can respond. And she is there. Great. Welcome, Teresa. Okay. And do I have Zach as well? I see 4, but I'm never sure if one of them is me or not. Anyway, that's great. And thanks everybody for being here. I would say getting up so early, but it's not really that early. Yeah, I was out shoveling snow already, so I'm pretty awake, obviously, even without my black tea. Today we're going to continue with waves, and we're going to go and look at wave interference and the Doppler effect. So we'll see if we get both those done, and then I got some problems I'm going to assign for later in the week. We'll either meet Thursday or Friday, probably not both, because some of that time I will send you an assignment, have you working on that instead, which is kind of what we're supposed to do with you. We're not supposed to meet with you every hour, every day, unless it's like a Lifestones course. When is our clausura? Good question. Do I know that? I'm not sure I do, but I do know it. Okay, I do know it. Did I write it down, Teresa? That's the real question. It's towards the end of May. I did this so it would be after your APs, okay? I don't have the date written here, but I can, let me write myself a note, Teresa, see if I can get it. So find clausura date. But it will be after your APs. I think that would be swell. Hey, and Zach is here. We are 4. We are strong. Nice. Okay, so find clausura date. Towards the end of May, Teresa. Okay, nice. All right, let's just review a little bit. I'll leave that there. So we talked about waves, and we need to know the wave equation, which was V was equal to, check your notes. And Sophia has it, the 27th of May, that's it. Yeah, 27 May. I remember it now. Thank you, Anne Sophie. 27 May. Yeah, so, and we'll review before then, and I hope that's exactly right. I hope we'll be back in school, obviously, by then, and it can be live because we have so many demos and so many labs I have to do with you guys. I miss you. You're a great class, and we have so much fun, and, well, we'll just do what we can live stream, okay? All right, so the wave equation was V, velocity equals h times h. So what was it for waves? I know you don't have Greek letters, but you can maybe write what they are. So what is the wave equation? So check back on your notes from, yeah, before winter break. Okay, what times what gives you velocity for a wave? For a wave. It's a rather important equation. And you're going to need it for the next problem set. So, yeah, and Sophia, it's frequency, but not divided by wavelength. I thought we had this. Let's see. Lambda times frequency. Yes, there it is. Okay, so lambda times frequency, F. And lambda is the wavelength, so you're going to multiply them together. So we got wavelength times frequency, okay? So that's wavelength in meters. And the frequency is in hertz. Hertz. And velocity is in meters per second. Now, V is equal to 3.0 times 10 to the 8th meters per second for light. Now, remember, there's a lot of types of light, okay? So it's not a light concept. Like visible infrared called IR, ultraviolet, you know that from sun tanning and not getting burned. Radio waves, believe it or not, are a type of light. It's going through you all the time. Luckily, they don't hurt you. Gamma, which can hurt you. X-rays, which can hurt you. Microwaves. Yes, it's a type of light in your microwave oven. Beautiful. All those are types of light. And V is equal to 342 meters per second for sound at like 25 degrees C, okay? So like room temperature. So if you have problems where they don't give you this, you need to know that's the one for light, that's the one for sound, okay? All right, so you'll need that. Good. Let's go to our first concept today other than that, unless you guys got a problem. And it looks like you don't, but you got a question. Is that why we call microwaves microwaves? Yeah, it is, because they're little. Okay, that's a cool question, Anne-Sophie. Radio waves are really big. They're like sometimes kilometers long. The meters, like the length is in kilometers or hundreds of meters. Microwaves are in the centimeters. Cute little microwaves. Okay, so yeah. Gamma rays are incredibly small, so they're like the size of a part of an atom. So they really vary in in wavelength. Okay, but they're all types of light. Okay, and visible is like 10 to the minus ninth meters. So that's also a nanometer. It's really, really small. Okay, so they vary. Generally, the bigger ones, the less harmful they are. The smaller, the more energy they got, because they got a greater frequency, as it turns out. So it's a greater energy. I didn't tell you that before. Okay, let's talk about wave interference. I may do this at school with you because I got some demos, but they're hard to see on camera. I may also try and find you a YouTube video for this. Okay, wave interference. It's more or less a pattern when wave hits wave. Pattern, and I'll say effects when wave hits wave. You can do it for any type of wave, including, well, not any type. The two types we had, transverse waves and compressional waves, okay? Remember, transversional waves like water waves or light, compressional waves like sound or some earthquakes are compressional waves. We're going to draw this on the board. It's fairly involved. You know what? I'm going to go and do it a different way because we have only a whiteboard and I can't like walk around and see you and help you. So let's do it first with sound, can we? Okay, so we're going to do wave interference with sound. And remember, sound is a compressional wave. Okay, let's pretend we got a wave. And what I'm going to do is I'm going to draw, remember there's compressions and rarefactions. For the compressions, if it's sound, remember the medium is what? What's the medium for sound? See if you remember what medium means too. What's the medium for sound? Somebody type it in for me. Not the small or extra large. What's the medium for sound? Hint, the medium for light is air or outer space, depending where the light is. What's the medium for sound? You still out there? Yeah, I think you are. The medium for sound? Nobody knows. Remember what medium was? What the wave is traveling through. So what is a sound wave traveling through? No, that would be unusual. A carpet? No. No, what does sound travel through? Like, what's it getting? What's the sound traveling through? Air. Thank you. Okay, right. Good. Thank you. Okay, so easiest way is thinking like, so I'm going to draw like air molecules. Ready? So here we go. So these are going to be the air molecules, and they're compressed together. And now I'm going to draw some further apart, and now compressed together, and further apart. Don't worry, I won't do this all day. And one last compression. Okay, so I got 3 compressions and 2 rarefactions, and my wave length is about from one compression to the next. So I tried to make it the same. Well, wave interference is when one hits another. When one hits another. So let's say we're going to add this one to the following. Okay, plus and in between we just got a rarefaction. Okay, obviously my 2 waves have very different wave lengths. I'm going to focus you in because I hope you can see that okay. Everybody got that? So I got one, the wavelength is from here to here. The other, the wavelength is much longer. It's from here to here. Okay, all right. Okay, so essentially interference means we're going to add them together and see what happens. Okay, if I got to get a compression hitting another compression, turns out that makes a really, I'll put like an equal sign, okay? Turns out if they add together, the effects add together, so I get a really impressive and loud compression. So if they line up, it's going to be very compressed, very loud. So make an extra compression with lots of molecules shoved in there. On the other hand, and let's write over that loud. Over here, if I get a rarefaction plus a compression, what do you suppose they might do if a rarefaction kind of lines up with a compression? Can you guess? What will happen if a rarefaction meets its opposite, a compression? what will happen to the sound? I know it takes sometimes a while for your typing to reach me, but I'll wait a few more seconds and see if you guys can kind of figure it out. You'll see why I'm telling you this in a second. Yes, Aunt Sophie, it would be quieter. In fact, it would be really quiet. What happens is this would be like dead air. This would be like the result is just normal air. Air without sound. Now, where it's loud, we could call this, it's got two names, okay? Now, let's see. All right, how do I want to do this with you? I've never taught it this way, so I got to think of the best way to do it. Let's give you this first. If a compression hits a compression plus compression, it's loud, and I get what's called an antinode. Antinode, N-O-D-E. But if I got a rarefaction hitting a compression, I get like things cancel out and I get what's called a node. I like to think node, no movement. Okay, so there's nothing special happening, so it's quiet if it's sound. So I got a node and an antinode in my drawing. Okay, let me jump to the application. Why am I telling you about this? Okay, the application is something that you might have. I've got a pair upstairs. How many of you or someone in your family have a pair of noise canceling headphones? Raise your hand. Okay, I have the Bose ones, B-O-S-E, and they're pretty darn good. And what they do is really cool. They have a little microchip in them. The microchip takes in the sound and sends out the opposite. So microchip sends out, it sends out really the opposite wave to what it hears. So that for every compression, there's a rarefaction, and every rarefaction, there's a compression. You know what I mean? So headphones send out opposite waves to what comes into the headphone. Result? You tell me, what do you think the result is? So you're wearing these things, the opposite is being sent out to what is coming in. Yeah. So it cancels out the noise. So what I get is what's called destructive interference. We're going to define these in a second, so don't get too upset. Here's one little spot of destructive interference where I had rarefaction hitting a compression. That's just one little tiny spot called a node. But the process is called destructive interference, and it's quiet. However, it doesn't let out, exactly, thank you, Ellie, the rarefactions and compressions cancel out, right? It does not cancel out voices. So if you're on an airplane, remember when we used to fly in planes? If you're on an airplane, it will not cut out like the steward or with a whatever they call them now, their voice, okay? Or the person next to you. Or if somebody's snoring, sorry, it won't cut that out, but it'll cut out the engine noise. If something is constant in the background, it'll sound really quiet. That engine noise is totally taken care of and it's nice and quiet. It helps some people sleep better. Okay? Okay, so voices come through. But can I say constant noises? Constant noises eliminated. There's the word. Eliminated. So if you live in an area with a lot of background noise and it's constant, you can wear those. If you live with somebody who snores, don't bother. They don't help. Any other questions? Oh, why doesn't it work with voices? Okay, with voices are too complicated, to be honest. So the machine cannot, and they're always changing. So the machine cannot instantaneously make with the microchip the sound that the voice is making because it's constantly changing as we talk. We don't even think about it, but that's what happens when we talk with the human voice and other sounds that it can't deal with. So we're just not droning. Maybe if you did something like this, Anne-Sophie, and I've never tried that, but maybe that would work. I don't know. Be interesting to do. Okay, that's kind of a messy board. Let's define what I mean by destructive and the opposite type of interference. Okay, any other questions before I erase here? We okay? How we doing? We're doing okay. Okay, so I'm gonna erase all this. I kind of need the whole board. Let's draw it with transverse waves. So let's say plus So let's say two waves are the same. Well, what's going to happen? You can just about guess. A crest is going to hit a crest that's going to make it bigger. Whoa! And then a trough will hit a trough and make it deeper. Whoa! Like that. So this would be like constructive interference, okay? Because it's constructive, it builds something, if you know what I mean. Constructive interference. Can I fit that word in there? You know what that is. So it's where crest hits crest, or remember the other part, the low part is called a trough. Trough hits trough. Okay? That's constructive interference. Another name you might read in some books is positive interference, okay? I'm positive that's what some books call it. Okay, so constructive interference. Let's do destructive. Okay, what's going to happen with destructive? Can you guess? I'll draw the first one. So I'm going to go plus, how about really poorly drawn. I'm sure their blessed men make fun of me, but too bad. Okay, so check it out. These are opposites. Crest, trough, trough, crest. What am I going to make? What's it going to look like? Exactly, the opposite. Exactly, Ellie, where the crest and troughs don't match. So what's going to form? Can you guess out here? Anybody? Describe what picture I'm going to draw. It won't look like constructive interference here. What will be the result? High meets low, low meets high. What will be the result? Yeah, nice. Exactly, Ellie. It just cancels out and makes a line. This happens with transverse waves like light and water. Okay? So that's destructive interference. With transverse waves, obviously with sound waves, right? Compression of waves, it just sounds quiet. Okay? And that's where a crest meets a trough. Or vice versa, but I won't write both. Or let's make it plural, where crests meet troughs. Oh, that makes a lot more sense. Then I get destructive, also called negative interference. You might have felt this either in a pool, swimming pool, or in a lake. You ever stand there and all of a sudden, like oddly, a wave comes up and like slaps you in the chin? You're like, where did that come from? Well, it might have been two waves from different spots that came together and interfered, and maybe a crest met another crest, and then right there was your chin and slapped you in the chin with a bunch of extra water. Or you might have not noticed it, but maybe it got shallower for just a moment where you were, and that was where a trough was hitting a trough. Okay? Okay, I'm going to try and find, I think, a YouTube video to show you that. I can show you it live, but I don't know when I'll meet you. I don't know what's going on next week. Yeah. Yeah, so that's kind of what's up with interference. I think I'm going to draw a more complicated version with you now. Okay, so hold on to your hats, all right? I'm going to also send you a file, I hope I remember this, that has like some rings for you to find the interference spots. Okay, but first we got to define a couple things. Constructive and destructive interference, these are called the processes. You'll see why I'm saying this in a second. In other words, like noise canceling headphones use the process of destructive interference, but the actual physical little spots are called nodes and antinodes. And sometimes you get both, and that's what we're going to draw now. Yeah, that is so true, Anne-Sophie. Yeah, I've had that happen there. Okay, so what we're going to do is we're going to make a couple of drawings. We're going to imagine we've got two pebbles. Ready? Boop. I'm going to drop two pebbles at the same time in the water. Bloop. Bloop. Where should I drop? Here. And we're going to make like little rings. You know when you throw a pebble, you got rings that come out? We're going to make rings come out. And I'm going to let a solid line You know what, I'm going to make this bigger. I'm going to make it bigger because okay, so let's make a solid line where the crest of little waves are. And let's make a dash line boop, 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 where the troughs are. Okay? Like that, probably. Okay, here we go. So let's say I'm just going to start drawing some, and I'd like you to draw this too. Again, I'll try and send you this file, but it's probably good to draw it once with me. Okay, so here we go. How big do I want to make it? Maybe one more, or at least a little ways over here, okay? So bum, 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 bum. Okay. And in between are going to be those are the crest, here's the troughs. Yes, I know this takes a while, but it's worth it because it does teach us something. So I do want to take the time to do it. Kind of wacky looking, huh? It's like a big tire or something, a big snail. I don't know. We're going to do another one now. Maybe I'll do the next one in blue. Not that it matters. And we're going to say they got the same wavelength, so I'm going to try and draw that out like the other one. I'm not doing a perfect job, but the way it's going to be. It's not bad. I've done worse. Maybe some others here, huh? Okay, when you get that far, stop. I know it's not easy to draw, but do your best, okay? And again, I'll try and send you this, so if you really screwed up, you can do it again on one that I send you, okay? All right, what we're gonna do is, how are we doing on time? We're doing okay. Um, sorry, quick nose blow. We're gonna mark every spot with a little red dot for me. That's an antinode. So these are the locations of spots. The processes are called constructive and destructive interference, but the spots are called the antinode, and that's where we're going to have crest hit crest or trough hit trough. Okay? Let's do those first. Let me show you what I mean. So anytime I got a solid hitting a solid, that's going to be an antinode. So I got a bunch of them. Bum, 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 bum. Mr. Why is there so many? Yeah, I know. Keep drawing. I know. Life is hard. Okay, so is that it? No, I got a couple more. And. If you got colors, it will make it slightly easier. I think I got them all. Okay, but I also want where trough hits trough. So now I want dashed hitting a dashed. Oh, darn it, I forgot my dashes. Ah! Okay, for the blue one, you got to go back and put in the dashes. Notice how I did that with the black? I forgot to do it with the blue. So in between the blue solid lines are going to be blue dash lines, like this. There's one here too that I forgot. It gets very busy, doesn't our diagram? It gets very busy indeed. But it will show us something cool at the end of the day. That's enough. All right, so once you get that done, then we're going to hit these spots. No, sorry. I'm back to the red. I'm going to hit the spots where a trough hits a trough. So trough hitting trough. So dash hitting dash, like there's one. And there's one, even if they're not actually touching, where they're going to cross each other. There's one. There's one. So do that with me. Yes, there's a lot of them. Because there's a lot of interference happening. Yeah, that's pretty good. I think I got them all. Sure tried. Okay, then, if you got another color, I'm going to use green, and I'm going to use that for, holy moly, yeah, we're doing okay. I'm going to use that for the nodes. These are little locations where I've got, you guessed her, a crest hitting a trough. So crest, trough hit, okay? So I want a solid hitting a dashed. Okay, solid line hitting a dashed. Okay, so here we go. And you're getting good probably. You can probably notice they line up. So just follow them and line them up. Oh, see, it's not as hard as you're thinking. They line up. They just go on and line up. Here's another one. And another. Are you going crazy yet? Here's another. Okay. Got a couple. A lot of them, huh? Okay, that's pretty good. You may have to watch this video again. I'm sorry if it's complicated, but that's the way it is to draw these diagrams. This is called an interference pattern that you're drawing, okay? Interference pattern. And it's a series of lots of nodes and antinodes. We get them with light, we get them with sound, we get them with all sorts of things. Interference patterns are really Not only are they found in nature, but they're found in technology a lot. For example, CDs, or the back of your CD is an interference pattern. That's how you get the music or data. Whoa, okay, now I'm going to really stretch your mind. We're going to connect some of these together. In other words, these antinodes really come out, and mine, okay, ideally, if I did this perfectly, I could use a ruler, but I can't because they're not perfect. They're going to kind of line up pretty good. So there's an antinode, and I'm going to write an A at the end of that. Oh, and there's one going down. Funny thing. There's an antinode. There's another one. I know, I've done this before. It's a big advantage. I understand that. You should get like a set of spiraling lines going out. Spiraling out from the center. Oh, yeah. Sometimes I have arty students, and they can do this really pretty quick. They seem to have an eye for this. It took me years to get so I could do it this quick. Now let's do some nodes. So I'm going to do the nodes in green. And they kind of come out from the middle too. Check this out. Oh, so there's a node. There's another one. When this one. And they should alternate. Oh. So it looks, when you're done, it's going to look like na 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 na. You know what I mean? Na 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 na. Same down here at the bottom. After a while, you can just sort of draw them in. You know what I mean? Whoa. It's an interference pattern. That's actually one of the best ones I've drawn in my entire life teaching. Wow. That actually worked out pretty good. There's some more little lines you can draw, but that's most of it. That's really, really pretty cool. So you should have like these alternating patterns of nodes and antinodes. And so you got constructive and destructive interference going on in different spots. This is one of the videos I'll try and show you. Because if I do this with water, it's so cool because the nodes are flat water and the antinodes are really, really up and down lumpy water, like bumpy water. So it alternates when you look at it. Flat, bumpy, flat, bumpy, flat, bumpy, flat, bumpy, flat, flat, bumpy, flat. So every node is pretty flat water. Every antinode is bumpy water. Yeah, that's an interference pattern. I'm really kind of pleased. Yeah. And we're about out of time, so I'm going to just keep talking here to the end of the hour because I want to give you time to do this. I'm going to send you another one like this and ask you to try and do the same thing we did here with the one I send you, okay? When will I show us the video? Let me look for that now, Zach. I'll try and find the video now, and I'll put it in the live stream for the Google Classroom. And I'm going to send this to you to work on as well. Okay? I'll try and send you the wave interference with water and see if I can find that on YouTube. Okay. Thanks, everybody. I'll put this on the website in case you want to look back at it again because it's kind of complex. And yeah, have a good rest of your week. I'll be in touch with you on when we're going to meet again, too. Okay? Be well.